This afternoon session, our first speaker is Bianca Viray from University of Washington, and she speaks on persistence of the Brauer-Manin obstruction.
Hey, thank you, David, for the introduction, and thank you. Is this on? Yes? Okay. Thank you, everybody, for coming in the hot afternoon. So today, as David said, I'm speaking on what I'm calling persistence of the Brauer-Manin obstruction. And just a caveat, this is all work in progress. When I get to a precise statement later, I'll say sort of exactly where I am. But I think so far it's interesting enough that it's worth speaking about, and hopefully you will find the same. OK, so where do we begin? Well, we've already seen in many of the talks this week, so that if X is a nice variety over a global field F, then we have a pairing between the adelic points of X and the Brauer group that goes to Q mod Z. And the rational points lie in the kernel of this pairing. So this goes to 0 for all rational points on X and all alpha in the Brauer group. Okay, so the set of adelic points orthogonal to the Brauer group, we denote X of AF Burr. That's the Brauer-Manin set, and it gives us an intermediate obstruction set between the adelic points and the set of rational points. Okay, and we've seen many talks about whether this explains everything or how you might other ways of interpreting this set. So what I want to focus on today is a slightly different question. So is if you're not just interested in the rational points of X over F, but say as you go up in a tower of fields, and you know that you have a Brauer-Manin obstruction over F, what can you say about whether this obstruction persists or not as you go up the tower? So this is my vague motivating question. So given X a nice variety over a global field, under what conditions say either on X over F or the extension, but not X over the extension, because I don't want something trivially true. So under what conditions can we say that an obstruction, a Brauer-Manin obstruction over F, survives under passage to L? OK, so here I'm just putting XL to make it clear that I'm also considering the Brauer group over L, not just the obstruction over L that comes from downstairs. OK, so that's my sort of main motivating question. OK, so let me just remark that if you consider this in full generality, this is hard and maybe even an unreasonable question to ask. You know, sort of implicit in this question is a sense that maybe you can hope to have a nice answer. And I think in full generality, we can't hope that. So, and even, I think this could be hard and unreasonable even when we expect Brauer-Manin to control the existence of points. So it's not just when it's not a strong enough thing. And so for instance, so if you have for a curve x with a Brauer-Manin obstruction, so hence no rational points, and that has high gonality, then the conjectures we saw yesterday predict that that this Brauer-Manin obstruction persists for all but finitely many. Low degree extensions. But you have to allow the caveat of finitely many. So you can have curves with no rational points, but maybe 1 point of degree 2 or 1 point of degree 3. Then we expect that this should be empty except for the field of definition of that particular degree 2 or degree 3 point. And I mean, OK, I suppose you could say is the condition is L equals exactly this field. But I think many of us think that I mean, that's probably out of reach for any time in the near future. OK.
You mean bounded degree?
Finitely many, yes, bounded degree. Low bounded. Right, yeah. So I definitely, you know, this is not a precise statement anyway, but low in contrast to high. OK. So, and then, OK, so this already is a caveat that just this question itself is maybe not well posed in full generality, but then on the other extreme, you could also try to modify this question. This is just asking about existence of an adelic point orthogonal to the Brauer group, but we've seen in these talks that's not the only obstruction that this provides. You can ask about this Brauer set being equal to the closure of the f rational points. So you could ask about that instead. So you could ask about the behavior of the Brauer-Manin obstruction, say to weak approximation under field extensions. So Liang has recent work where he constructs examples. So shows that if you have the f rational points being the closure of the Brauer set downstairs, then this does not necessarily imply that it's the closure under the extension. OK, question? Oh, thank you. Just get carried away with the not equals everywhere. I think, and I think he's here, so maybe you can clarify. I think it's like Chatelet surface bundles and Should I repeat? Yes. Do you want to say it louder?
So it's a figuration over a curve for which the general cipher is a Chatelet surface.
OK. Yeah, Chatelet surface bundle. So great. OK. So no, because I'm going to specialize in a minute that will take care of that. But you could modify this question in many ways. OK, so what I want to do is focus on a case where we already, for other reasons, think that there should be a reasonable answer to this, and then see whether we can actually prove that in this case. So where the motivating question is expected to have a reasonable answer. Okay, so I'm going to take X over global field F to be a del Pezzo surface of degree 4. Okay, which is given as the intersection of two quadrics inside of P4. Okay, so geometrically, this is the blow-up of P2 at 5 points, but not necessarily over the ground field. So we can have a Brauer group and can have Brauer-Manin obstruction. So what do we get here? So say we have a Brauer-Manin obstruction over F. Okay, so then by definition of the Brauer-Manin obstruction, we get that we have no rational points over F. But then because X is given by an intersection of two quadrics, we can apply the Ammer-Brummer theorem. And we get that X has an F rational point. Well, because this has no F rational points, then that means the quadric fibration has no section, which is equivalent to just saying that the generic fiber has no F of T point. Okay, but now this is just a single quadric now over F of T, and so Springer's theorem about odd degree extension says that this happens if and only if the generic fiber has no sections over L of T for some L over F odd. Okay, so then we can carry everything back through here, and so we get that. So this is Ammer-Brummer again. So we get to conclude that the del Pezzo surface of degree 4 has a point if and only if it has a point over an odd degree extension. And then,
so that's for any L over F odd?
Any L over F odd. And then here we have a conjecture of Colliot-Thélène and Sansuc that predicts that the Brauer-Manin obstruction is the only obstruction for del Pezzo surfaces. So here we should have that there is a Brauer-Manin obstruction. Okay. So for quartic del Pezzo surfaces, the answer to this question should be very nice, and it should be you just have to look at the degree of the field. If it's odd, then the Brauer-Manin obstruction should persist. Okay, so that's what conditionally we want to prove today. And so since it's in progress, just to be precise, I'll put expected. And again, when I get to the guts of it, I'll explain what is missing. Okay, so X is a quartic del Pezzo over global field F. And I want to assume all residue fields are sufficiently large and X has good reduction at all places above 2. Okay, so then under these conditions, if you have a Brauer-Manin obstruction, oh, yes, sorry, that's unclear. All residue fields of F. Yeah, not related to X, just F.
You mean all? So you're always going to be split times.
Yes, so actually, so I was going to say this after let me finish writing the theorem, then I will specify. For all L over F odd. Okay, so I think the condition sufficiently large is actually just going to be that they're greater than 1. They have size greater than 1, which would always be true. But there's some point in the proof where I just use the, right now, I just use the Weil bounds to get that they do have points. But they're points in an open locus of a P2. And so I think I don't have to remove that many things. I think if I go through what I'm removing, I should get rid of this. But I haven't done that part yet. So yeah, so this may be removable. Okay. So in some sense, okay, I mean, maybe it's not surprising that this holds, but you can view this theorem as evidence for this conjecture. So if we want evidence for this conjecture, what can we do? Well, we can either construct, so the conjecture is that it goes both directions, but of course the other one. So we can either look at varieties with non-empty Brauer set and then try to construct a global point. That's in the spirit of what Jonathan was doing in his talk. Of course, he was working with more complicated varieties, but generally that's a difficult problem because somewhere out of thin air, or usually out of some element of SHA that you show as trivial, you have to produce an F-rational point, and that's often hard to do. So then the other thing you could do is you could try to construct a variety that has no points and then show that it comes from the Brauer-Manin obstruction. Of course, it's hard to come up with obstructions. That's part of the problem. So this is some way of sort of building an obstruction. I mean, yes, we expect somehow it's going to come from the obstruction that you have down here. But there's nothing in this argument that is using the element. I mean, these theorems that I wrote, Ammer-Brummer and Springer's theorem, those are just theorems for general quadratic forms over any field. They're not using anything about reciprocity or Brauer groups or anything like that. So, okay. All right. So to get this theorem, well, basically from a combination of things, many things that are already known, this translates into a purely local problem for local fields. So let's first see how this works. Okay, so for a del Pezzo surface of degree 4, the Brauer group, mod Brauer F, or the possibilities, have been completely classified. I think this was first done by Swinnerton and Dyer. But you basically, well, yeah, the geometry is simple enough that you can completely do this. And so the possibilities are that it's either trivial, z mod 2, or z mod 2 squared. And then Colliot-Thélène and Punin, in a paper from 2000, showed that if you have a quartic del Pezzo surface, then if you have a Brauer-Manin obstruction, then there is a single element that causes the obstruction. And so in their paper, they went through this argument using Ammer, Brummer, and Springer's theorem, and then asked whether, if you know that this is empty for this alpha, is the restriction of this element up to L, giving you the obstruction over L. Okay, and because of restriction, co-restriction, and because the Brauer group is completely two-torsion, this is essentially necessary in order for this theorem to hold. I mean, the only part where it might not completely be true is in the case where you have z mod 2 squared, all of the elements give you the obstruction, but only one element gives you the obstruction when you pass to an extension. But I think if you saw this, it would be pretty good odds that, okay, we should prove that that element causes an obstruction when you make an extension. Okay. What theorem? Oh, this is for a del Pezzo surface of degree 4, as I've written it, but they also prove it for cubic surfaces. For cubic surfaces? I guess what I wrote doesn't say anything about the two torsion, but yeah, so for cubic surfaces, they prove that this is true and that the element alpha has to be of order 3. And then for quartics, they also show that alpha has to be of order 2 in the Brauer group, not just in the quotient. Okay, so now our question, so the motivating question that I just erased, under this translation, it becomes, let's see. Is given x, dp4, over a local field k, little k, and alpha in the Brauer group of x, such that the evaluation map of alpha is constant, is evaluation map constant on an extension. Okay, and even though, so for global fields, we care about odd degree extensions. If you have an odd degree extension of a global field, then that can give you a degree 2 and a degree 1 extension of a local field. So in this translation, you actually need to do this for every extension. Okay, and so from now on, K will always be a local field. I'm going to assume that the residue characteristic is not 2. And I'm going to let F be the residue field and pi a uniformizer. Oh, I want a non-Archimedean local field. I don't have to worry about anything for Archimedean ones. Okay, so this question had been considered previously in some earlier cases. So this is true in the cases that x has good reduction. And for this condition, you don't need it to be a del Pezzo surface. So this, sort of in varying levels of generality, this has appeared in a few places. in Martin Bright's work. And then I think in full generality, it's stated in a paper by Colliot-Thélène and Sansuc from 13. And we also know it when, so if you take your intersection of two quadrics, you naively spread it out over the valuation ring. And if for that model, so if this model is regular and the special fiber is what's called a singular del Pezzo surface, so has only isolated non-conical singularities. And it's not of type 4A1 and 2A1, A3, then the answer is also yes in this case. And this is also due to Martin Bright in a paper from 2015. Okay. But we also know that you can have this constant Brauer class when you have worse reduction too. It's not that this is where it's known and that's maybe the only place where we expect it to hold. In fact, one of the first examples of a del Pezzo surface of degree 4, I'm trying to write so hard so it's visible from the back, but I'm destroying like many pieces of chalk in the progress. Okay, so one of the first examples due to Birch and Swinnerton-Dyer so they give a del Pezzo surface given by the equations BW equals x squared minus 5y squared, B plus W, B plus 2W equals x squared minus 5z squared. And they show that this has a Brauer-Manin obstruction to the Hasse principle, so it's constant everywhere. But if you look at the reduction at 5, we get a union, geometrically, we get a union of 4 hyperplanes that all meet in a line. Right, because it's just a cone over an intersection of 2 quadrics in P2. So, okay, so that's like very, very bad reduction. So we can't hope to control this by just saying, okay, this only happens when you have good reduction or very mild bad reduction. Okay, so oh, sorry. Yes, 4 planes. Thank you. Thank you. So yeah, a union of 4 planes meeting in a line. Right. Okay. So to prove this theorem, or at least the way I am proving this theorem, there are sort of 2 competing things that we want to hold, sort of that are in tension with one another. So I don't know whether it's a need or a want, but anyway. So on the one hand, we want our model of x that gives us a good understanding of the Brauer classes of the elements of Brauer X mod Brauer K. Okay, so concretely, as algebras that we would use to compute the obstruction, I want some way of writing down X that allows me to do this. And so for this, we're going to use earlier joint work with Anthony Varelli Alvarado. Where we heavily use the presentation given as an intersection of two quadrics. And we study the degenerate fibers in the pencil, and we use them to give us a very nice representation of the elements in the Brauer class. But on the other hand, we want to understand, so we have this Brauer class, we needed to compute the obstruction, so sort of having it as an algebra helps us. But on the other hand, we also know that computing the evaluation, that depends on the reduction type of the model that you have. Okay, so the possible singularities that you can get for a Del Pezzo surface of degree 4 when you reduce, or the types of singular intersections of two quadrics that you can get, that is well understood. So Corey and Softsman have a complete list of all the quartic Del Pezzo surfaces with isolated non-conical singularities. There's 15 of them. You can study sort of when it has a one-dimensional singular locus, if it's reducible, all of those things you can sort of, it's a long list, but you can make a list. But that's sort of abstractly the type of singularity that appears. In Corey and Softsman, it's sort of done locally around each singularity. It doesn't, you don't have an idea of how those singularities are reflected in the pencil of quadrics for the quadratic forms. And you also don't know, okay, that's what the special fiber looks like, but then how does it sit in the model? How far away from being regular is it? What is happening there? It's sort of, and if you try to like look at it naively and just take that list and then sort of deform it, you get this sort of horrendous combinatorial explosion of like what can happen. So we don't want to just do it naively. So what do we do to satisfy both of these ideas and find a method that sort of works well together with them? And so at this point, I would like to thank the organizers for their amazing scheduling of the talks, particularly before at least I had even sent him my abstract, because the answer here is to use minimization that Mikhail talked about in his talk. Okay, so this is minimization, or so this is also called semistable. Well, let's see. Semistable models. That's the terminology that Kolar uses, and I use an extension. So this was done by Kolar for hypersurfaces. So we don't have hypersurfaces here, but Tian extended this to intersections, arbitrary dimension, but intersections of two quadrics. Okay, so maybe let me come back to the details of this, but just the idea is it tells you sort of particular So it gives you a condition just in terms of some weight vectors that tells you numerical condition, which tells you when something is unstable. And if it is unstable, it gives you, then knowing that gives you a way to make it not unstable for that particular weight vector. So just like Mikhail talked about, you might have to do this over and over again, but this is a process that can be done. So Tian was using it to prove that intersections of two quadrics of dimension at least 3 satisfy the Hasse principle over global function fields. So he uses this to control the singularities. We don't get as tight control for quartic del Pezzo surfaces, but you get enough control to make the cases manageable. Yes?
When you say to approach this, do you mean to do an analog of those results or to use those results?
Oh, yeah, sorry. I mean to prove this theorem.
Okay.
So, yeah, in very shortly, basically what we do is classify sort of when you can have constant evaluation over your ground field sort of in a very constrained way, and that gives us enough control that then we can actually prove that it remains true for the extensions.
So you're using the results of
No, we don't use them. Well, I use this one, so I don't have to reprove that, but you'll see the classification. This doesn't naturally come up as one of our cases, but I can show you where it is in our classification. Okay. So maybe let me just say one more word about this. So as we saw earlier, this works for hypersurfaces of any degree, and it also works in any dimension. Here, this works for intersections of two quadrics. I think it wouldn't get you as much for curves, but it works in any dimensions, but they have to be quadrics. So Tian says in the paper that he doesn't know how to extend this to complete intersections of two higher degree things, or maybe when one is a quadric and the other is higher degree. And the problem is that this stability condition, it's very good at checking the presence of linear spaces in your variety. So we saw that in Mikhail's list. You know, detecting instability was telling you that you had a line appearing with high multiplicity. So if you have two quadrics that aren't a complete intersection, that you have a component that's codimension 1 instead of codimension 2, that component has to be a linear space. And so the presence of it will violate one of these stability conditions. But if you have two forms of higher degree, then they could have a component of higher degree, and it's not obvious how you could use that extra component to violate a stability condition. So that's exactly the problem, why it has to be quadrics. Okay. And let me just make one more remark. Sort of explaining, just a comment, expanding on what I said verbally, that the evaluation really depends on what happens in the specialization. So there's this theorem. This is a special case / combination of work of many authors. I think, so Colliot-Thélène, Bloch, Colliot-Thélène, let me just do a few of them. Saito, and then the last piece was by Saito and Sato, I think from 2013. So and this is for any geometrically rational surface. So if X has a regular model, script X for which the purity theorem holds. And we'll hear more about that this afternoon. Say just purity. Then the Brauer-Manin pairing gives an isomorphism. Okay, and all of this is still over local field. Gives an isomorphism from the group of 0 cycles of degree 0 to just the Hams from Brauer x to Brauer script x plus Brauer group of k to Q mod z. Okay, so if you think about what we're trying to prove that if something gives you 0 on all 0 cycles of degree 0 that are differences of rational points, then it should just be 0 everywhere. So it should just be the 0 map. And what this theorem tells you is that the only way that that is the 0 map is if the element alpha spreads out to be in the Brauer group of the whole model or a constant algebra, plus a constant algebra. Okay, so solving this problem is basically equivalent to doing this, which would then show you that, well, yeah, so then you get that every 0 cycle is represented by a sum of rational points.
So
Yes?
This is a local for local field.
Local field. Local field. Yeah, everything from there over is local field. Oh, x. Okay. Okay, so I just quickly need to introduce some notation from this paper with Tony. So what we show, so if you have an intersection of two quadrics, so from this you can look at the pencil of quadrics like I did at the beginning, and you can let S be the degeneracy locus. Of the pencil, so inside of P1. So this is a reduced subscheme of degree 5 because I'm assuming that x over k is smooth. And so what we show, and then so for all points in this degeneracy locus, I want to define this epsilon t to be the discriminant of this degenerate quadric. Well, how do we consider it? So it's a rank 4 quadric inside of P5. So if a rank 4 quadric inside of P4. So if I just naively take its discriminant, will be 0. So I restrict to some hyperplane where it's smooth and take the discriminant there. And then that's some non-zero number, and its class mod squares. It doesn't depend on the choice of hyperplane. Okay, and so what we show in the paper is that the elements in the Brauer group are in bijection with degree 2 subschemes of this degeneracy locus, where if I take the product of the norms of these epsilon t's, this is a square. And then some other conditions, and there's sort of an equivalence relation on these pairs, but broadly That's what. So for a Brauer class, I can associate one of these script t's. Okay, so I'm going to let x in P4 of O be a minimized or semi-stable model in the sense of Tian of a smooth del Pezzo surface of degree 4 x over k. Okay, so the generic fiber is Roman x, then the specialization is there. And I want to assume that we have a k rational point. Oh, okay. I guess, okay. For my question, I needed to assume that I had a k point. Otherwise, it's not going to be true. Assume that this is non-empty. So if there exists an element in the Brauer group, so two torsion element, such that the evaluation is constant on x of k, then at least one of the following holds. Okay, so either we have good reduction, our alpha is split by an unramified extension of k, the degree 2 subscheme corresponding to alpha is non-reduced mod pi, or the last condition is that the special fiber has a singular line. And we can be more precise. So there are three possibilities for if it has a singular line. So one is that it's a cone over a nodal genus 1 curve. One is that it's a cone over a cuspidal genus 1 curve. And one is that it's, well, it's not a cone, and there's a unique way that you can get that. I don't know a better way to describe it. And so in the nodal case, then there are other conditions on what happens to the Brauer class, but I'll just leave them out. But you just completely classify what is possible. Okay, and so we're sort of, you can see here that we're really using the understanding of the Brauer group and the understanding of the regular model in tandem. I'm not trying to give a sort of a complete list of all the reduction types and saying what happens to the Brauer class there. I mean, okay, maybe it could be done with someone that has more patience than I do, but it quickly gets out of control. Okay, and then once you have this very complete understanding, of how these constant Brauer classes can arise, in all of these cases, okay. Let's see, generically. In all of these cases, the evaluation map remains constant after any extension. Okay, so this is the star for my in progress. So definitely it goes through for 1 and 2, and it goes through sort of in the general case in 3 and 4. So if 3 and 4 both don't hold, and if like you have a singularity that requires 2 or 3 blowups to resolve, then I haven't chased down all of the details. But sort of in the nice case, so when it has a singular line, then this model will never be regular. So you do have to deal with extra components, but it's sort of at a one-step process, it's not too bad. And I think there's a better way to phrase the argument that I currently have, and I'm trying to find that before I do the harder cases. Yeah?
Do you know if the converse of the theorem is true? That if you have this type of production is constant?
Yes. I mean, that's basically what I have to prove here. Oh, no, sorry. That's not right, because I also assume that it is constant to prove these. Let me think. No, it's not definitely true in this case. So you could have a singular line, and then exactly on these components that I talked about, sort of it can. So in all of these cases, it's constant on the component from the naive model. So on the special fiber of the naive model, but that's not a regular model. And so it can still be non-constant on some of the extra components. Well, OK, it can be a different, it's constant on the components, but a different value than it is on the other components. OK. So maybe I will just, in the last little bit, give just a brief flavor of the proof. OK, so I'm just going to focus on the case 4. So for 1, I just cite the result that's known. 2 is also not that bad of an argument. These cases handled by the 2015 paper of Martin, they all fall into this case. And that's what he shows in his paper. He shows that if you have a regular model with only isolated non-conical singularities, and it's not of these types, then the Brauer classes are all split over an unramified extension. And that doesn't happen for 4a1 and 2a1a3. And then in those, you can have constant or non-constant Brauer class, and it depends on this condition. So it's exactly captured by that, the missing piece, the cases where it's not necessarily always constant. OK, so let's assume that 1, 2, and 3 don't hold. So we know we have bad reduction, that our Brauer class is not split by an unramified extension, and that the 2 points remain distinct when you reduce mod pi. So, OK, so let me just say what I said again. So T mod pi is a reduced degree 2 subscheme. And pi divides this discriminant of the rank 4 quadric. So that means when you reduce, yes, yeah. OK. So this is how I wrote it initially. So this is ramified. So in the pencil defining the special fiber, there are 2 distinct rank 3 quadrics. So these ones, you know they have to drop rank. And then the semi-stability condition tells us that they can't be rank 2. So semi-stability allows us to show that there are no rank 2 quadrics in the pencil at all. So they have to be rank 3. So then we have two distinct lines. So we get two lines, well, L1 and L2, that are the singular loci of these rank 3 quadrics. So then we can look at what happens with these two lines in P4. So if they're the same line, then our reduction is a cone over an intersection of quadrics in P2. That can't happen by semistability. So then they either meet in a point and you're a cone over a genus 1 curve, or they're two distinct lines, and you can either show that the reduction is either going to have a singular line, or it's going to have isolated singularities of type 4a1 or 2a1a3. So it just like completely complements the characterization that Martin had already given. Okay, so from this, you get a handful of cases that you have to consider. So in some of them, you contradict the fact that the Brauer class was constant. So for instance, if you have a cone over a smooth genus 1 curve, you can't have constant evaluation there if these conditions are not satisfied. Yeah. Okay, so then from these cases, you get this. And now we need to take from this case and show that the evaluation mean stays constant. And so as I alluded to, sort of from the equations, it's not very difficult to show that it stays constant on the component in P4F. But there are non-regular points there, and you have to show that the evaluation remains constant at k points that reduce to those non-regular points. Okay, so the semi-stable assumption tells you that x is regular at the generic point of the singular line. And you get that it's not regular at a degree 3 subscheme of the singular line. Okay, so in the general case, there are 3 distinct points on the special fiber that are not regular points of the total space. And amazingly, this degree 3 subscheme is, so this is a shadow of, we have another degree 3 subscheme floating around. The degree 3 subscheme that we have floating around is S minus the degree 2 subscheme that is giving us our point. So we had these 5 degenerate quadrics. 2 of them are giving our Brauer class. There are 3 remaining other ones. And so right now I just have sort of a calculation that shows this in the families. I have like 3 families to consider, and they're just the same. So that's what I was saying, that I think there's a better way to explain this, which will make the extension easier. So right now I'll just call it a shadow. It's like sort of the same equation. And the residue at the components above these points is a shadow of these epsilon t's, which we know a lot about. So the things that we want to compute end up being things that we already understand, and we understood them in this joint work with Tony to try to understand the Brauer group. Okay, thank you.
Questions or comments?
So, okay, given these examples and also the sort of examples you talked about at the beginning where somehow it's quite delicate whether there's a rational point or not and you would expect sort of find a list of exceptions,
yeah.
Are you willing to speculate about what are the classes of varieties where you would expect this kind of question to have a reasonable answer?
No. So the most I'm willing to speculate is, so I think this, so what I want to do, so I think this shows a method of doing it. It required sort of a lot of understanding of some subtle things, but we have this understanding for other surfaces. For instance, we have it for cubic surfaces, and there we don't know exactly when to expect that an obstruction over your ground field, which extensions it should do. So I think working this out will maybe give you a prediction, but yeah, I don't know in general. And also I should say, so here for quartic del Pezzo surfaces, it just reduced to this purely local question about the evaluation being constant. This isn't always true. So already for, well, OK, the fact that this implies the persistence of the Brauer-Manin obstruction, that is not always true. And so for del Pezzo surfaces of degree 2, there are examples where you actually need 3 different Brauer classes. And so you can have that they remain constant, but that they no longer give an obstruction if you have sort of splitting, enough splitting at a place where, sorry, I'm saying this badly. OK, so that you have 3 different non-constant elements that combine to give an obstruction, but then their interaction disappears when you have enough splitting. So.
More questions?
So this is maybe a little bit more like a comment, but I think what your proof gives is that a Brauer-Manin obstruction to points implies a Brauer-Manin obstruction to 0 cycles of degree 1.
Oh, yes. I didn't mean to write that, but it does.
Well, I think your proof gives that.
Right.
Because you're using a Brauer class from the base field.
Yes.
So maybe a way to answer the earlier question is that you would, for this kind of method to work, it would be a variety for which rational points are equivalent to the existence of 0 cycles of degree 1, maybe something like this.
Right, yeah, so I guess it's telling you that, yes, that's a good point. So it's the same Brauer class that we're studying, and so in cases where sort of the degree of the elements that are giving the obstruction are related to the degree of the variety, then by restriction, co-restriction, you know for extensions prime to that degree, those Brauer classes will it will be an isomorphism of the Brauer groups. Or, sorry, it will remain injective. Yeah.
More questions?
So what is surprising is that if you take a del Pezzo surface of degree 4 with a rational point,
yes.
Any 0 cycle of degree 1 is rational equivalent to a rational point. Okay?
Yes, okay.
So it's quite surprising that, so I mean, I would feel, so if you start with you have your extension of odd degree, and you have element in the Brauer-Manin set upstairs, and you push it down, pi lower star.
Okay.
You're going to get a 0 cycle of odd degree downstairs, which will be orthogonal to the Brauer group downstairs. So if we could show that you can replace the 0 cycle odd degree by something of degree 1, you'd be finished. And I mean, for instance, suppose the Pezzo surface of degree 4 has a point in a quadratic extension. Yes. Then you're finished. Because you have this 0 cycle of degree 1 ever locally of degree d. D is the odd degree, okay, d. So you push it down, you get the 0 cycle of degree d. And then you can subtract something, a multiple of 2, and you get something of degree 1 on the local field.
Right.
And that's rational equivalent to a local point.
Okay.
And that's going to be orthogonal to the Brauer group downstairs. So you produce an element. So what I'm saying is that this argument, if I might be mistaken, seems to give that if you take a del Pezzo surface of degree 4 of a number field, and you take an odd degree extension, and you assume the Brauer-Manin set upstairs is non-trivial, and you know there's a point on your del Pezzo of degree 4 in the quadratic extension, then then the Brauer-Manin set downstairs is not empty.
Okay.
I mean, using this fact that over any field, you have this very special, this is maybe to answer the question we had over there, that which kind of varieties can you expect this kind of result?
Yeah.
Well, you would want a positive answer to the similar question for 0 cycles of degree 1, and you want a second result, which would be purely algebraic, that any 0 cycle of degree 1 is rational equivalent to a rational point.
Right.
And there are very few of the latter. But depth of degree 4 have this property.
Other questions? Well, if not, let's thank Bianca again. And next talk is at 4.